In this video, we are going to talk about concavity and the second derivative. All right, so first off, we'll start with the definition of concavity. So let f be a differentiable function on an interval I. Okay, if the graph of the function f lies above all of its tangent lines on I, then f is said to be concave upward or concave up on I. All right, so let's take a look and see what that means. So here I have a function graphed out. The function is in red, and I have the tangent line at the purple point here graphed out. That's that blue line. So over here on the right side, if you take a look at all of the tangent lines, you can see that this blue tangent line, right, is below the graph. So the graph is above its tangent line. So you can see if I move the tangent line around a little bit, then the graph of f is still higher up than the tangent line. So that's what it means to be concave up. So you'll notice where it's concave up, it kind of bends upward a little bit, although that's not a precise definition at all. But you can see also that it's above the blue tangent line. All right, going back here, if the graph of a function f lies below all of its tangent lines on I, then f is said to be concave downward on I, or concave down. All right, and so if I go over here and kind of look at this left half of the function, it is bending down. If you take a look at the tangent lines, you'll notice that all of the tangent lines, right, over on this part, the blue tangent line is above, right, the graph. So the graph of f is below its tangent line. Okay, so that's an example of concave down. All right, so it's concave down over here, and then over here it's concave up. All right. All right, so what we want to be able to do is to determine the intervals on which a function is concave up and the intervals on which a function is concave down. So that's pretty straightforward. If the function has two derivatives on the interval I, if the second derivative is positive for all x in the interval I, then the graph of f is concave up. So positive second derivative on the interval means that the graph is concave up, and if the second derivative is negative or less than 0 for all x in the interval I, then the graph is concave down. So this situation is very, very similar to the situation that we had for increasing, decreasing. And the only difference really is that we are looking at the second derivative. That will tell us about the concavity. So the work is pretty much the same as it was to find where a function is increasing or decreasing. Okay. The one thing to me that is a little bit more difficult is to than it is in the increasing decreasing situation is to understand why this second derivative tells us about the concavity. Okay, so that's what the next slide is about. So if I have a twice differentiable function f, it's twice differentiable in the interval I, then these statements are going to be equivalent. So first is f is concave up on I. All right. And so the key to understanding this is to notice, if we go back over here and look, right, so over here we're concave up on this side of the graph. And what we're going to be noticing is as I move this tangent line, take a look at its slope. All right, so here the slope of the tangent line is negative, right? And then you can see that as I move to the right, that the line is flattening out a little bit. So what that means is that the slope is getting bigger. It's still negative, right? And somewhere, like right at this point here, the slope will be 0, although I have a hard time getting Desmos to go on there. Let's see, 2 point. No, too much. See if I can move this. Yeah, that's a little bit easier to control. So right about here, the slope would be 0 in there. All right, so no longer negative. And then as I keep moving to the right, you're going to see that the line keeps tilting up like this. And so what that means is that when the graph is concave up, that means that the slope of the tangent line is getting bigger. The slope is negative here, negative, but getting bigger, negative, but getting bigger. And then right there at the bottom, the slope is 0. Then it becomes positive, right? And then this line's tilting up. That means it has a bigger slope. So the slope of the tangent line is increasing when the graph is concave up. And that is the real key to understanding that. So if f is concave up on an interval I, that means that the slope of the tangent line is increasing, right? The slope of the tangent line is getting bigger when it's concave up. The next step is to understanding this is what gives the slope of the tangent line. Well, that is the derivative, right? The derivative is the solution to the tangent line problem. So if the slope of the tangent line is increasing, that means that the derivative is increasing on the interval I. All right, and then in the last section, we learned that a function is increasing when its derivative is positive. Okay, so if the derivative is increasing, that means the derivative of the derivative is positive, right? And then the derivative of the derivative is just the second derivative. All right, so the key to understanding how the second derivative gives you the intervals on which a function is concave up and the intervals on which it is concave down is understanding this chain of events right here. Okay, and to me, the real, if you understand everything that came before, the real bridge is understanding that when a function is concave up, its tangent line, the slope of its tangent line is going to be increasing. And a similar chain of reasoning follows for concave down. So over here, the function is concave down, and as we go from left to right, you can see that the blue line, the slope is getting smaller. Right now the slope is positive. Right, so if I move to the right a little bit, you can see that the line rotates down again. So that means that the slope is getting smaller. At the top of this peak, it will be 0, and then it will go negative, right? So when the function is concave down, right, that means that the slope of the tangent line is decreasing. So there's a similar chain of events for being concave down, although I didn't actually list those out. All right. Okay, the last thing that we'll need to talk about before we start getting into an example is the inflection point. An inflection point is a point on the curve, on the graph, at which the function is continuous and the curve changes concavity. So by changing concavity, I mean it changes from concave up to concave down, or changes from concave down to concave up. All right. So that is very similar to what we did for local max and local min when we talked about increasing, decreasing, only this time we are doing it with the second derivative instead of the first derivative. Also, there's no distinction, right, between changing from concave up to down or down to up. We just call it an inflection point. So when we go to classify the critical numbers of f prime, we will, before, with local max and local min, right, the critical numbers were either local max, local min, or neither. In this case, the critical numbers of f prime will either be an inflection point or not an inflection point. So there's only two choices here. Because the inflection points are generally a lot harder to spot than a local max or local min, right? Local max, right, like this, it just kind of stands out. It's a local high point, or a local min, it stands out like this. Whereas an inflection point, right, it's kind of hard to spot. It's somewhere in here. Okay. Let's see, where is that at? I think it's about, I think it's like negative. All right, so 1.67 there. So the inflection point here is 67 f of, or approximately the inflection point. So it's right around in there where it changes from concave down to concave up. Okay. So you can see they're just a little bit harder to spot. They don't stand out quite as much as a local max or local min. And you know, if I turn this upside down, right, that's a place where it switches from concave up to concave down. It doesn't really look any different, right? This inflection point doesn't really look any different than the other case. So we don't really break those down like we do local max, local min. And so you can see right about at that blue point right here, then you can see it switches from being concave down to concave up like this, right? All right, so that's what we're going to be doing in this section. The work that we're going to be doing to determine where function is concave up, concave down, and to classify or to find all the inflection points. That work is going to be pretty much exactly the same as we did in the previous section on increasing, decreasing local max and local min. It's almost exactly the same. Instead of doing it with the first derivative like we did in that section, in this section for concavity and inflection points, we're going to be doing the same thing but with the second derivative. All right, so that's it for this video. In the next video, we will take a look at a specific example.